The topic, tangents and secants to a circle. We all know what a circle is, a round shaped figure which is equidistant from its center. Now coming to the introduction, the word tangent has been introduced because when different structures were studied along with respect to a line, then the line was either touching or intersecting or non-intersecting, is how we conclude. But before we enter into this topic, let's come with the introduction of tangents and secants to a circle. Now to start with, the straight lines, which we already discussed in the previous session. The straight lines had three different cases. Let's recap with the straight line cases which we have introduced in the previous sessions. Now the straight lines were identified either to intersect, the line L1 is said to intersect L2, or the second possibility was the line L1 was parallel to L2, and the third possibility was that the line L1 and L2 coincide. So there were three different cases we have taken in case of straight lines, either intersecting or being parallel or non-intersecting or coincident, intersecting at infinitely many points. So as we had three different cases arising out of two straight lines, also we have a curve and a line coming out with three different cases. The possibilities of a curve and a line arising with three different cases was, say for example, if I study the two lines intersecting at a unique point, then if I have a curve, so this is the curve C, then the line is either going to be intersecting. In this case, we say a curve is intersecting the line, and in this case, we say a curve is touching the line, and in this case, we say the curve and the line are non-intersecting. Is how we have three different cases which we can compare with the three different cases of straight lines. So the possibilities are that the curve and a line may intersect, may do not intersect, or may touch at one point, or touch, the curve and the line may touch. So these three different cases have risen to the topic of tangents and secants to a circle. Today we are going to study about the circle and the different possibilities of a line which cuts the circle, do not cut the circle, or touches the circle are the three cases which we are going to study in the session of tangents and secants to a circle. So let me consider a circle and a line and see how different cases arise as seen in the previous session. So considering a line and a circle, initially to start with, the case 1 where I have a circle with a suitable radius and then I have a line which does not intersect. So this is the line L and this is the circle which I denote with this. So for a circle and a line, here the possibility is that the line does not intersect the circle. Now the second case is where I have a circle and a line which cuts the circle. So here the line cuts the circle, here the line does not cut the circle or does not pass through the circle. And the third possibility is that a line touches the circle, is how we study the three different cases. In this case, the line touches the circle. So here we have three possibilities of non-intersecting, intersecting, and touching. So usually I refer this as non-intersecting. I refer this as intersecting, of course, intersecting at 2 points. And I refer this as touching because the line touches the circle here, the line intersects the circle here, the line does not intersect the circle here. So in this case, these two are a very special case which we take into consideration because when the line and the circle do not intersect, then we mathematically we assume that the line and the circle have no relation because they do not intersect. In case of this and this, we have many mathematical properties which we are going to study as geometrical understanding of the line and the circle, intersecting and touching. To come with the intersecting circles here, if suppose I have the 2 points P and Q where the circle is intersecting, then this line segment PQ is called the chord or the secant of the circle. The chord or secant of the circle is what we call the line segment PQ. So for an intersecting circle, we have the chord and or the secant for a given circle. So here PQ is called chord or secant of the given circle. So the line segment PQ is called the chord or secant of the given circle. And as I identify, the chord or the secant is always less than the diameter, because if I take the diameter, then the diameter is the maximum chord. So geometrically here, I understand that the diameter is the maximum chord. The length of the diameter is the highest chord out here. So if I take a note here, diameter of circle is the maximum chord of circle. The word maximum because the diameter is that length where we have the highest segment of the circle. And if it acts as the chord, then diameter of circle will be referred as the maximum chord. So coming to the chord and secant, let's switch on to the touching circles, where if suppose I say the line touches the circle at say point P, then I call the point P as the point of contact, and the line is said to be a tangent to the circle. It's very important that when a line touches the circle at single point, then the chord is 0 because there is no secant or chord. Therefore, length of chord or secant is assumed as 0 in case of a line touching the circle, because this P and Q tend to one point is how we understand. So when P and Q tend to one point, then we get a tangent. So therefore, for touching circles, we say that the two circles touch when chord tends to 0. When chord or secant tends to 0, then we get a tangent out of a secant. So an intersecting concept reduces to touching concept if the chord reduces to 0 or the secant reduces or tends to 0. So this two converge at a single point, and here in this case, if the chord tends to 0, line L is called tangent. The line L is called tangent, which is very important property out here. And L is called point of contact. So in case of touching concept or the touching case, the line L is called the tangent to the circle and point P is called the point of contact. And how do we get the touching case? When the intersecting circles have the secant or chord tending to 0, then I get the touching case. And in that case, the line L is the tangent and here point P is the point of contact. I'm sorry, it is not L, but the point P, which is the point of contact. The point P, which is identified here, is said to be the point of contact. So these are the three cases through which we understand a line cutting a circle, not intersecting a circle, cutting a circle at 2 points and touching the circle, of course, at 1 point. Is how we understand the three cases of a line and a circle in its geometrical concept. So let's exclusively study the topic of tangent of a circle as defined in the previous session, the case 3 of the line and its circle taken together. Now what is a tangent? Let's recap with the already discussed topic out there. we see that a tangent is a line which touches the circle. So simple definition for a tangent is a line or a straight line which touches the circle is called a tangent. Now with this definition of a tangent, I have a fair question to all of you. How many tangents can we draw to a circle is the biggest question. So how many tangents, if suppose I take a circle with a suitable radius, then there are infinitely many points on the circumference of the circle. Therefore, at every point I can draw a tangent. Say for example, I would like to draw a tangent at this point P. Now how do I draw a tangent at this particular point P on the circumference of the circle? I straightly draw a line which touches the circle, and this is the line which touches the circle. Therefore, this line L is said to be the tangent. This is said to be the tangent at P. Now I have some point Q, then I do not call the tangent at P as at Q as this, because the tangent refers to that point where the line touches the circle. Now I call this as tangent at P because this line touches the circle at point P. If I wanted to find the tangent at Q, then I have to draw a line which touches the circle exactly at the point Q. Then I refer to that line which touches the line circle at point Q as tangent at Q. So for example, I have this touching at Q. Then this is called the tangent at Q. Is how we understand the tangent connected with a circle. Now with this concept, I have an important note which says that there are infinitely many tangents which I can draw. So when I go with the first note, it says that there exist infinitely many tangents at infinitely many points on the circumference of the circle or on the circle. Because there are infinitely many points on the circumference of the circle, there are infinitely many tangents you can draw, each of the point referring to the respective tangent or the line drawn at that point to the circle, touching the circle at that particular point. Secondly, this point is very important in its own geometrical understanding. So let's write the statement and just support on whether that is true or false. There are only two tangents which are parallel to each other. Now, as we have discussed in the first note, there are infinitely many tangents to the circle. Now, the fixed point is that there are only two tangents which are parallel to each other. That means there exist only two tangents which are exactly parallel to each other and to the same circle. So in this case of, if I take a circle with suitable radius, then if I draw a tangent at this point, say A, then I have exactly on the opposite side of the diameter, exactly on the other end of the diameter, I have a tangent which are parallel. If this is L1 and L2, then in this case L1 is parallel to L2. Therefore, when I draw a tangent at one point of the circle, then the other tangent is parallel exactly on the other end of the diameter. Therefore, for AB as the diameter, if my tangent lies at point A here, then exactly on the other end or the other extreme of the diameter AB, I can draw a line, then only the two tangents are parallel. You cannot have three pairs of tangents parallel in the circle. This is a very important geometrical property which connects the parallel lines and the tangents for the circle connected through the geometrical property of the diameter of a circle. In this case, L1 is parallel to L2, which are the tangents at A and B. And not only that, interestingly, A and B are the extremes of the diameter. So take any diameter, draw the lines to the ends of the diameter touching the circle. Those two lines, which are the tangents, must be parallel, is how we understand the second note in geometrical understanding. Now let's see a theorem which connects the relation between the tangent and radius. The tangent and radius are always said to be connected because they are very much associated geometrically in their own understanding. So let's identify the relation between the tangent of a circle and the radius of that particular circle taken into consideration. So let's see that through a theorem and then prove on the supported statement what we're going to take here. So let's start with the theorem which says that the tangent of a circle at any point of contact is perpendicular to the radius of the circle. This is what we are going to prove in the theorem, that the tangent is always perpendicular to the radius of the circle. So the statement to be completed with the tangent of a circle at any point of contact is perpendicular to the radius of that circle at the same point of contact, is how we understand the statement of the theorem. To understand the statement more clearly, let me just draw a diagram and see how the statement reads or is understood in the geometrical understanding. So if I take a tangent at any point, say I consider the point P here as the point of contact between the line which is the tangent and P. T is the tangent and P is the point of contact. Then the theorem says that the tangent is perpendicular to the radius of that circle at the same point of contact. Now this is very important because there are different infinite radius we have on the circle, but this tangent is said to be perpendicular to that radius which passes through the point of contact. So there's only one radius which passes through point of contact. All the different radii pass through the different points on the circumference of the circle. So on these infinite points, there are infinite radii, and there's only one unique radius which passes through the point of contact. And this radius is said to be perpendicular to the tangent at that point of contact P. So we had to prove for the radius perpendicular to tangent. So let's try to prove using the various mathematical properties that radius is perpendicular to tangent. So let's start with the given part of the theorem which says that consider a circle with center O. Let P be the point of contact. Let P be the point on the circle where xy is the tangent, is what I have considered in case of the given. Therefore, using this given concept, I have a circle where the center is O, circle with center O, and P is a point on the circle. Say this is the point P on the circle where xy is the tangent. So at that point P, xy is a tangent which comes like this. So this is how the given concept is reduced to a diagram. That implies from the given part, if I join OP, then what will OP be? That implies OP is equal to radius of the circle with center O and passing through P. Now, as we have already discussed in the given part that there's only one radius which passes through point P, I want to consider that particular radius out of the infinite radii where OP is the radius which I am going to consider here. Is the radius of the circle with center O and passing through the point of contact. And passing through the point of contact P is how I understand the given path. Now, once the given concept is converted into the diagram, next comes on what I need to prove. So let's take the RTP, the required to prove path, which says that clearly I need to prove that the radius is perpendicular to the tangent. That is, the radius in case of that diagram being OP passing through P, and the tangent, which is XY, is what I'm going to prove in my theorem. So this is what I need to prove in its mathematical understanding. So let's see the proof of the theorem utilizing the diagram and few of the mathematical properties. So coming to the proof. Now, to start with the proof of the previous theorem, we need to understand that the proof is by contradiction. That is, I assume that the radius is not perpendicular to tangent and I prove a contradiction in mathematics. Then our assumption becomes wrong. So this kind of a proof is generally referred to as the proof by contradiction. So here the proof is by contradiction. To make a note of the proof. So let's assume that let OP be not perpendicular to the tangent XY. So remember, OP is referred as the radius and XY is referred as the tangent. Now, because I need to prove that the radius is perpendicular to tangent, my proof by contradiction says that I assume that OP is not perpendicular to XY, and then I come to the assumption which is wrong. So finally, my assumption being wrong makes the original assumption that OP must be perpendicular to XY. And such kind of proofs are called the proofs by contradiction. So to start with, I assume fairly that OP is not perpendicular to XY, where this is the radius passing through P, and this is the tangent at P. So identifying the radius and tangent, let's see how we can proceed with the proof. So because OP is not perpendicular to XY, let Q be a point on XY such that OQ is perpendicular to the tangent XY. So let me take one of the point Q which is perpendicular and prove by contradiction. Therefore, since Q is a point on XY such that OQ is this, implies clearly that if I take a point Q on XY, say I take somewhere here, because already there's a point P on the circle, then in this case, let me join OQ. Now here, I make a note that since OQ is perpendicular to XY and Q is a point on XY, that implies Q lies outside the circle but on the tangent XY. This is a very important note I need to make because geometrically I say that Q lies outside the circle to support, because if suppose Q lies inside the circle, then what happens? So for example, my Q lies inside the circle, then because Q is a point on XY, tangent is always a line which touches the circle, so Q cannot be inside. If it is inside, then the line also must be inside. where this line acts as the secant. Therefore, Q cannot be inside the circle because strictly it lies on xy, which is the tangent. If it lies inside, you get a secant. So therefore, Q lies outside the circle, since the reasoning is very important here, because since Q lies on the tangent xy, which touches the circle, that is, if Q lies inside the circle, then Q lying on xy and inside the circle implies xy is a secant to the circle, because it acts as the secant. If Q lies inside, then it cuts the circle in two parts, which is an absurd, which is not possible because simply xy is a tangent. It's not possible because xy is a tangent to the circle. But when we assume that Q is outside, as we have proved through the previous part of the proof, then if Q lies outside the circle, then clearly OQ should be greater than OP, because since Q lies outside the circle on the tangent xy, therefore OQ should be clearly greater than OP. As you can see here, P lies on the circle and Q lies outside, therefore this must be greater line segment than this, as can be seen through the diagram. This is greater than OP. But I think this is not possible, because that means our assumption that OQ is perpendicular to xy is wrong, because if OQ is perpendicular to xy, then OQ must be the shortest distance. But here I have one more shortest distance other than this. That means our assumption that OQ perpendicular to xy is wrong, since OQ greater than OP implies OQ is not the shortest distance. The shortest distance. Therefore, OP must be perpendicular to xy. This is how we get the radius perpendicular to tangent. Therefore, OP must be perpendicular, because OQ is not the shortest distance. Therefore, you take any point out other than P, it lies outside, and therefore that point makes us OQ greater than OP. Therefore, OP is the shortest distance. Therefore, OP is perpendicular to xy. Since OP is the shortest distance from O to xy. So this proves that the radius is perpendicular to tangent. So for any circle with center O, the radius passing through the point of contact must be perpendicular to tangent. This is how we conclude the theorem, the proof by contradiction. So normal is associated with tangent because a normal is a line which is said to be perpendicular to the tangent. Therefore, taking the definition, a normal is a line perpendicular to the Therefore, if I take a circle with center O and a tangent to P, then this line passing through the center or passing through the point of contact is called the normal. So therefore, if I take a line which is passing through this, then this is called the normal of the line. So this is referred as normal to the line. So any line which is perpendicular to tangent and passing through the point of contact is called normal. So here, this is the tangent at P to the circle, and this line passing through the point of contact and perpendicular to the tangent is called the normal. The tangent perpendicular to the normal. Now, construction of a tangent. How do we geometrically construct a tangent to the circle at that particular point on the circle using the geometrical instruments or the geometrical knowledge is what we're going to discuss for the session. It's quite easy because construction of a tangent is based on the recent theorem which we have discussed, which says that the radius is always perpendicular to the tangent at that particular point of contact of the circle. Therefore, using that property, let's see how a tangent can be constructed for a circle with suitable radius. So initially, let me start with the steps. So my step 1 says that draw a circle with center O. So I just draw a circle with center O is what is my step 1. Then I take a point P on the circle, any point P. Say for example, I take a point P on the circle so that I join OP. Clearly, OP is the radius which passes through the point P is how I get. Now for any point P on the circle, OP is the radius, and I assume this as the point of contact, then I want to draw a tangent to that circle. Now we all know that since the radius is perpendicular to tangent, so if I wanted to draw a tangent at the point of contact P, then I need to have exactly 90 degrees drawn from OP. So I put the protractor here, and then from this protractor, I just try to measure the angle which is 90. Exactly marking the 90 degrees and just extending that line, I get the perpendicular line which is called the tangent. So this is how we construct the tangent to the circle at the point P, where my step 1 is drawing a circle with center O, and then my step 2 is joining O and P, and my step 3 is taking a protractor and exactly putting that at P and marking 90 degrees. And then extending the line along that 90 degrees, I get a straight line passing through P and perpendicular to OP, where this is called the tangent which is constructed for the given circle. This is how the tangent is constructed for a given circle with suitable radius. It's very simple. Construction of a tangent using the geometrical properties. Radius perpendicular to tangent. Now this construction makes me clearly understand that for every point there's only one tangent, because if I take the point on the circle and draw the tangent, I do not have two tangents which can pass through the same point. So this construction makes me come out with the learning outcome that at every point on the circle, we can draw one and only one tangent to the circle. One and only one tangent, which clearly is evident through the construction as made. One point on the circle, only one tangent. No two tangents can be drawn from one point on the circle, is how we come with the learning outcome through the construction of a tangent using the geometrical knowledge. Now this topic is a continuation of the previous session of construction of a tangent. Interestingly, the difference being that I have to construct a tangent to the circle whose center is not known. So how do I locate the center for a circle and then find the tangent is the biggest challenge for this topic. So when the center is not known, obviously we don't know the radius, and hence we cannot base on the radius to draw a perpendicular line which will be the tangent, because radius is perpendicular to tangent. Now in this case, let's see how we can construct a tangent though the center of circle is not known. So in this case, let me take the steps which involve a circle. Let me take a circle whose center is not known. So I take the point P on the circle, say the point P on the circle is this. On any part of the circumference, I take here the point P on the circle. Then I join to get the chord. So let me take another point Q on the circle such that I join so that PQ is the secant or the chord of the circle. So with the construction of P and Q joined, with Q being a point on the other side of the circle, then with this I try to create the radius. How do I get the radius from this circle? Since we know that angle in a semicircle is 90 degrees, that is, when I take a circle and just divide it exactly half, then any angle made by the semicircle will be 90 degrees. Using the concept of angle in a semicircle is 90 degrees, this becomes the diameter. Therefore, I try to construct a semicircle using the property of angle in a semicircle is 90 degrees. Therefore, when I join P and Q, PQ being the chord, I can get the diameter this using, I can get the diameter AP if I can construct the angle PQA as 90 degrees. So immediately I put my protractor at Q, and then putting my protractor out here, I try to measure the angle 90, exactly the 90 degrees, and then extend. This out here. So when I extend this line tends to cut the circle at the other side as, say, I take it as R. I take this as point R. Now I get this to be 90 using the protractor. The measurement of angle is 90. Therefore, PQR is 90 degrees. Immediately, when PQR is 90 degrees, RP tends to be the diameter, because this is the property in a semicircle. Since the angle in a semicircle is 90 degrees, when I join this, I get this to be the diameter. So RP is the diameter of the circle. Now this being the diameter, exactly the middle of RP, take the measurement and cut the measurement into half, I get the center of the circle, which can be created from the angle in a semicircle. So dividing this into two parts by using the perpendicular bisector concept, I get this, and then more than half, and then I get the perpendicular bisector, which gives me the center as O. So this center O will give us the radius, which is nothing but the radius. And from radius, I can construct the tangent because radius is perpendicular to tangent. Therefore, put the protractor out here and then measure the angle. Then clearly, I get a line which is a tangent to the circle. So it's quite interesting that even though we don't know the center of the circle, initially we try to identify the center of the circle by joining the chord PQ, by locating some point Q on the other side of the circle and joining PQ, and then drawing a 90 degrees angle. We get a point, third point, which cuts the circle here, and then join PR, which is the diameter. Now to get the center of the circle is nothing but exactly half of the diameter. Therefore, I take more than half, and the compass is used to construct the perpendicular bisector. So with the perpendicular bisector, I get the center which intersects the perpendicular bisector with the diameter. Now once I know the center, I know that OP is the radius, and therefore using my protractor out here, I measure the angle 90 and pass through P. Therefore, I get the radius perpendicular tangent. Therefore, this is how the tangent is constructed from the circle where the center of circle is not given. Is how we construct the tangent for a circle with an unknown center. Length of tangent. What do you mean by length of tangent for a circle? Because tangent is a line which extends infinitely on the left and the right. So what do we mean by length of tangent is the biggest challenge of the question. So to start with, let's take a diagram. I take a circle with center O and say I have my tangent at the point P. Say at P I have a tangent. Now, suppose I have this tangent which extends infinitely on the right and left. Then the length of tangent from, say, a point Q to the point of contact is said to be the length of tangent. That is, the length is referred as the distance of the point of contact from the desired point. So if Q is any point outside of the tangent or outside of the point of contact, then we have to find the distance between P and Q, which is called the length of tangent. So if I have this to be clearly the radius which is perpendicular, and this is say D, the distance from the point to the point of contact, then clearly when I join OQ, I get a right angle triangle OPQ, as can be clearly seen in the diagram. Therefore, length of tangent here is PQ, and I take this as D units. Now, since OPQ is a right angle triangle, immediately the Pythagoras theorem comes into existence. Triangle OPQ is right angled. That implies by Pythagoras theorem, I clearly get OQ square equal to OP square plus PQ square. So by Pythagoras theorem, I get OQ square equals OP square plus PQ square. Then I take this, let me take this as L, not D. So if I take this as L and I take this as D, let's see what exactly I get by substituting in the Pythagoras theorem. So to continue with, I get OQ square, which is clearly OQ being D, reduces to D square equals. So here in place of OP, I have R, which I'm going to substitute on the right hand side as R square. Similarly, my PQ, which is clearly L, reduces to L square, is what I get when each of OQ, OP, and PQ are substituted from the right angle triangle OPQ. Now, to continue further, because I need to find the length of tangent L, which is the topic of the session, therefore I take R square plus L square on the left and D square on the right, so that because I need to find L, my L square will be D square minus R square. That implies L is plus or minus root of D square minus R square coming as the root, but I don't take the negative value because length cannot be negative. Therefore, taking the positive value, L is root of D square minus R square units. So the length of tangent is given by the formula root of D square minus R square, where D is the distance from center of origin to the point outside the circle, center of circle to the point outside the circle, and R is the radius of the circle. So length of tangent can be found out if I know these two dimensions. Then the length of tangent is quite easy using the formula root d squared minus r squared units. Now let's see the number of tangents which can be drawn to a circle. As we have seen in the previous case that when I take an external point, we have got the length of tangent from the point of contact. This is how we continue into understanding the number of tangents which can be drawn to the circle. Now there are three different cases which I am going to consider here for the number of tangents. The three cases being that if the line is cutting the circle, if the line is not cutting the circle, or if the line is touching the circle, then we'll see how different points are arised. Say for example, I have a circle with center O. Similarly, I have a circle with center O, and I have a circle with center O. Now for these three different circles taken with same center O, let me take the three cases where I take the point P initially lying inside the circle. I have the point P which lies inside the circle. I have a point P which is on the circle, and I have a point P which is outside the circle. So these are the three different cases where the point P is inside the circle, on the circle, and outside the circle. So clearly I understand that in this case I cannot draw any tangent, because when P is inside the circle, you cannot have any tangent which can be drawn at any part of the circle. Therefore, no tangent can be drawn through P to the circle. This is how I understand the concept of a point lying inside the circle. Let's shift to the next case where the point P is on the circle. Now in this case, clearly I can see that there is one tangent which can be drawn to the circle passing through P. Therefore, in this case, I have one and only one tangent can be drawn through P to the circle as given here. So, no tangent and one tangent is how we get from the first two cases. Now let's shift to the third case where the point is exclusively outside the circle. Now since the point P is outside the circle, I can clearly see that the number of tangents I can draw from here are two. One coming out, passing through P. I have one tangent here which is T1, and I have another tangent which passes T2 are the two tangents which I can clearly see passing through P to the circle with center O. So in this case, I see that for any point outside the circle, there are two tangents which can be drawn. Two tangents can be drawn through P to the circle. So is how we understand the three cases where if P is inside the circle, there is no tangent which can be drawn through P to the circle. If P is on the circle, then there's only one tangent which can be drawn through P to the circle. And for P outside the circle, there are two tangents which can be drawn through P to the circle, as can be clearly seen through the respective diagrams. 2, 1, and no for inside, on, and outside the circle is how we understand the number of tangents connected with three different cases of the point P to the circle with center O. Now let's see a theorem which connects the third case of the previous session. As the third case says that if P is a point outside the circle, then there are only two tangents which can be drawn from an external point P to the circle with a suitable radius. Now, since these two tangents can be drawn, the theorem says that those two tangents, the lengths of those tangents will be equal. The theorem exclusively says that for for the pair of tangents drawn, the pair of tangents drawn from an external point P, an external point P, external in the sense outside the circle, from an external point P to the circle, have equal lengths, is what the statement. The statement clearly says, to understand more through the diagrammatic representation, geometrically we understand that if this is a circle with, say, center O, then from an external point or a point outside the circle, if I draw, we know that clearly we can draw only two tangents, tangent 1 and tangent 2. Then if I take this as A and B, then mathematically the statement says that the two tangents will have equal length. That is, this will be equal to this, implies PA is equal to PB, is the property we identify in tangents connected with circles. Two tangents are equal if they are drawn from an external point to the circle. So let's see this proof of the statement through each of the construction of the given required to prove constructions and the proof. So let's see the proof of the given statement. So let's continue with the given part of the theorem. So in this case, I consider a circle with center O is what we consider initially. That is, I take a circle with center O. Now let P be a point outside the circle. So it's next, let P be a point outside the circle. So let me take the point P, which is outside the circle. Now, secondly, I come to drawing the tangents from P to the circle. Clearly, I see there are two tangents which can be drawn. As I see here, this is one of the tangent which is drawn, and this is another tangent which is drawn out here at A and B. So here I see that implies PA and PB are tangents to the circle which is considered with center O, is what I get out here. Then thirdly, I join AO and OB, which can be taken as the construction. Here the construction is join OA and OB the radii. Now OA and OB are the radii, therefore they must be equal. Now since their radius is equidistant from any point to the center, therefore OA is equal to OB is what we have. Also, I join OP because this helps me in the further proof of the given statement. So I just join OP using the concept of O join with P. Now let's use some of the geometrical properties to understand on how we can prove that this is equal to this. So here finally, the thing what I need to prove is that there are equal tangents, or the lengths of the tangents are equal from an external point to the circle. Now since PA and PB are the tangents from external point P to the circle with center O, therefore I need to prove that PA is equal to PB. This equals this is what I need to prove in the proof of the theorem. So let's required to prove is PA is equal to PB is what I need to prove using the geometrical properties, the various geometrical properties in mathematics. So let's see the proof of this theorem continued. Now let's see the proof of the theorem where I need to prove that PA is equal to PB. So in this case, as I join OA and OB, which are equal because they are the radii of the circle, similarly, we know that they are perpendicular to the tangents because we know that radius is perpendicular to tangent. So first, OA is equal to OB initially, which is identified because they are same radii for the circle. Secondly, I find that these two are 90 degrees because radius is always perpendicular to tangent. Is the theorem what we have seen in the previous sessions. Therefore, OA is perpendicular to PA or AP, and OB is also perpendicular to PB is what we identify in either cases, because by theorem radius is perpendicular to the tangent is what we have seen in the previous sessions. Therefore, this perpendicular to this and this perpendicular to this. Now, as I see the diagram here, I identify two triangles here, OAP and OBP are two triangles which are part of the entire diagram. So I would like to take these two diagrams and show that they are congruent. My intention of showing the congruency will help me in finally making conclude that this is equal to this. So let's see how the congruency leads to the outcome of the proof or the final proof. So therefore, consider triangles. The first triangle here is OAP. Consider triangle OAP and triangle OBP are the two triangles which I consider. Now, as I clearly observe that the right angle out here is PAO, which is 90 degrees. Therefore, angle PAO of the first triangle is equal to angle PBO of the second triangle, because each one of them is 90 degrees, as already proved that this is perpendicular to this and this is perpendicular to this using radius perpendicular to tangent. So one of the angle is 90 degrees, which is right angle, is what we have from the two triangles. Similarly, I see that PO is the common length of the two triangles, therefore they are equal. That is, the length PO is equal to the length PO itself, because this is the common side for both the triangles, therefore they must be equal, common for two triangles. Interestingly, we also observe that this is the hypotenuse for both the right triangles which we have out here. So PO is the hypotenuse for the triangle OAP and PO is the hypotenuse for the triangle OBP, as can be clearly seen that this side is opposite to 90 degrees in either of the triangles. Therefore, this leads to the hypotenuse, right angle, hypotenuse, and let's see one of the side. Now, as I see in the two triangles, I see that OA is equal to OB because they are the same radii as given with the reason. Therefore, OA is equal to OB since same radii. We have already discussed in the previous session of this. So this is the side property. This makes us clearly reflect on the right hand RHS congruency as we discussed in the topic of congruency in the previous sessions. Since RHS is one of the congruency, therefore, since the right angle is equal, the hypotenuse are equal and one of the sides are equal, therefore, the two triangles are said to be congruent under RHS congruency. Is how we conclude the congruency of two triangles using RHS congruency property. Therefore, continuing from the previous part of the proof, I see that these two triangles are congruent by RHS congruency. Therefore, by RHS congruency, triangle OAP is congruent to triangle OBP as can be seen clearly. Now, since the two triangles are congruent, therefore their angles and sides must be equal in all respects. Therefore, the congruency makes us understand that all the sides and all the angles must be equal in their own respective manner. Therefore, the congruency gives us PA is equal to PB, and not only that, we also identify that angle OPA is equal to angle OPB as can be clearly seen. The angle bisects. Now this PA equal to PB implies the lengths of tangents as can be clearly seen from an external point to the circle are equal. That implies the lengths of tangents from the external point P to the circle are equal, is what we conclude with the statement of theorem, is how we get to the congruency, RHS congruency of two triangles connected with the lengths of tangents equal. So whenever we draw an external point, we assume that these two lengths are always equal for any point outside the circle from where the two tangents are drawn. Also to note, there's a property we identify that PO bisects APB. Because of this property, also we get from the congruency that the line segment PO bisects angle APB. So angular bisector, what we call. So PO is the angular bisector of angle APB, is also which is identified from the congruency from the geometrical part of understanding each of the properties of congruency. Hence proved. Now let's see how we can construct the tangents from an external point exactly through the geometrical understanding or through the geometrical instruments to an accuracy to its best. So how do we construct the tangents from an external point? So let's see the construction in a stepwise process. So initially, let me assume a circle with a suitable radius and center O. So therefore, if I have a circle with center O, then I know that I can draw two tangents if I take an external point P outside the circle. The third case, as we have already discussed. So for a point P, there are two tangents which can be drawn from the external point P. Therefore, we don't know where exactly the two tangents can be drawn. I just construct using the geometrical properties. So to identify the points A and B on the circle is what is entirely about the whole construction. So how do we locate the points A and B on the circumference is the biggest question here in a successful construction of tangents from an external point. Therefore, let's take an external point P from where the two tangents have to be constructed. So here I join the points O and P using a ruler. So joining the points O and P, I get a line segment OP which is from P to O. Now I find the midpoint of PO using the bisector concept. I take the compass which is more than half and I just cut the arcs out here and this out here. And once I cut the two arcs, I join them so that the intersection will give me the midpoint of the line segment OP. So using the compass concept, taking more than half and cutting the bisectors and then joining the line of the point of intersection of the two bisectors, I get the perpendicular bisector of OP, which in turn gives me the midpoint of OP. Now once I get the midpoint, I just take the measurement of OM as the radius and draw a circle. So using the compass, I just draw a circle with as this. I draw a circle with this as the radius. Now with OM as radius, once I draw the circle, I clearly identify that this bigger circle cuts the smaller circle at 2 points A and B. The points of intersections of A and B are nothing but the located points where if I draw a line through PA will be one of the tangent for this circle with center O, and if I draw a line PB, then this will be the other tangent for the circle with center O. That is, when I take this point P and join P with A, and then I join P with B, I get the two tangents from PA and PB. Of course, PA equal to PB from the previous theorem is how I can draw the two tangents from an external point. So let's recap with once again on how we have constructed the two tangents using the geometrical properties. Initially, I take a circle with center O and I take the external point where from the external point to the center I draw a line, which is the line segment PO. Now once the line segment PO is considered, I locate the midpoint of PO by using the perpendicular bisector concept. We all know that we take the compass more than half and cut up and down, and that line passing through point of intersection cuts exactly in the middle of and perpendicular to OP. Now once I locate the midpoint M, I try to take OM as radius, and using a compass I draw an entire circle passing through O and P. Obviously it passes through P because these two distances are equal. They act as the radius for radii for the bigger circle. So drawing the circle, I get the bigger circle which cuts the smaller circle at A and B. Now the circle which cuts at A and B are located as A and B, and then joining P and PA and PB are nothing but the required tangents for the circle with center O. So once I get the tangents PA and PB, they are nothing but exactly the two tangents which can be constructed from an external point. But the biggest question here is why? Mathematically, I want an evidence on why this bigger circle cutting at A and B exactly makes us evident that these two are the tangents is the biggest question. Max is not about assuming, Max is about proving the results. So how do we prove that what we have taken are mathematically valid for being the tangents? Why is it that this circle cutting here makes the tangents is the biggest question for here. So let's see. Clearly, when I take the bigger circle, my radius, my diameter here is PO for the bigger circle. Now since PO is the diameter, if I just join A with O, I get this to be 90 because this acts as the semicircle for the bigger circle. Therefore, with M as center and OM as radius, I got the bigger circle where I join AO, I get triangle PAO is a right angle triangle right angled at A because angle in a semicircle is 90 degrees. Therefore, this angle will be 90. Now, indirectly, I have the radius perpendicular to tangent because angle in a semicircle is 90 degrees for this bigger circle, but if you take the smaller circle, I get the same angle to be the radius which is perpendicular to tangent. Because this angle is 90, this must be a radius and this must be a tangent to that radius. Is how we conclude using the concept of radius perpendicular to tangent. So mathematically, since the angle in a semicircle is 90 degrees, therefore that 90 degrees helps us in locating this to be the line which is perpendicular to the radius, and hence by the theorem radius perpendicular to tangent, this must be a tangent to the radius. or to the circle with the radius passing through the point of contact. And hence, the two tangents are PA and PB, is how we conclude. Now let's see some properties of tangents. Already we have discussed about many properties in tangents. Radius is perpendicular to tangent, and the length of the tangents are equal from an external point to the circle, is how we have seen some of the properties of the tangents connected with the circle. Similarly, let's see some extended properties of the tangents, which are also very useful. Initially, to start with, the concentric circles. So let's take two circles which are concentric to each other, that is, concentric in the sense with same center. If two circles are concentric, implies the two circles are with the same center. Now in this case, let me draw a chord for the bigger circle. Say this is the chord or the secant for the bigger circle AB. So the chord or the secant of the bigger circle AB makes us understand that this is a tangent to the smaller circle. I take the chord for the bigger circle in such a way that it touches the smaller circle in this manner. Now since AB is the secant which touches the circle, the smaller circle, therefore I understand that AB is the chord or secant for the bigger circle, but AB is the tangent to the smaller circle because it touches at, say, point P. Is how I understand. AB is the chord for the bigger circle and AB is the tangent for the smaller circle, tangent at P. Now let me join OP. Now I need to prove here that P bisects AB. That is, the point of contact in this situation always bisects the chord AB, is what we need to prove here. That is, when I have the point of contact for the smaller circle must bisect PB. That is, I have to prove that PA is equal to PB, is what I need to prove in case of the concentric circles, the bigger circle and the smaller circle. So for this, let's join AO and BO so that I get this perpendicular to this and this perpendicular to this, because radius is perpendicular to tangent for the smaller circle. So here the construction is, so here I join OA and OB. Also I join OP. Now in this case, my required to prove is PA equal to PB. Therefore, let's see how we can prove this using the two triangles AOP and BOP. So to start with the proof of the statement. Now for these two triangles, let me take, considering triangle OAP and triangle OBP, clearly I see that these two triangles are congruent, as I can see that one of them is 90 and one of them is the common side and the third side is the radius. By SAS or RHS congruency, I have these two triangles congruent. That is, if I start with OA is equal to OB because of same radii. Is the same radius, therefore this must be equal to this. Next, my OP is equal to OP because it is the common side for the two triangles. Therefore, this is because of the common side property. Similarly, angle APO is equal to angle BPO, which is equal to 90 degrees. That is, angle APO is equal to angle BPO, which is 90 degrees. Since radius is perpendicular to tangent is what we have already discussed as the theorem. Now clearly I see that this is right angle, this is hypotenuse, and this is one of the side, which again makes me remind of the RHS congruency through which the two triangles OAP and OBP are congruent. Therefore, for this triangle, by RHS congruency, I can prove that triangle OAP is congruent to triangle OBP, are the two triangles which are congruent to each other. Now therefore, because the two triangles are congruent, they are equal in all respects with angles and sides. Therefore the sides must be equal. Therefore this triangle with the side AP must be equal to the other triangle with the side PB. That implies PA must be equal to PB, is what we have proved through the congruency of two triangles. Therefore PA is equal to PB implies P bisects AB, is what the statement concludes, is how we get. Therefore, when I draw a chord to the circle, then the other concentric circle where the chord acts as the tangent will exactly be the midpoint. That is, this bisects, P bisects AB, such that PA is equal to PB, is what we have proved in case of this theorem. So let's take the next property, the extended properties of tangents, where the property says that if I have a circle with an external point P, then I can draw two tangents. So let's draw the two tangents to the circle, one of them here and one of them here, this and this. Now here I need to prove that, let me take this external point as E and my center as A and this as P and Q, so that my points are P and Q. Now if I join P and Q and then join with this and this, then I had to prove that this angle is twice of this angle, is what we need to prove. So let's see how we need to prove this. So if I consider a circle with center O and A is any point outside, I can draw two tangents from the external point A, that is AP and AQ are the two tangents. So using the two tangents, let's see how I had to prove. Angle PAQ is twice of angle OPQ, or it is also twice of angle OQP, is what I need to prove using the diagram. So this is the required to prove part. So how do I do the proof? So clearly I see that from A I have AP equals AQ. Therefore triangle APQ is isosceles triangle because two of its sides AP and AQ are equal. APQ is clearly an isosceles triangle since AP is equal to AQ. Now let me take this as theta. Now clearly I identify that if this is an isosceles triangle, this angle and this angle must be same by isosceles property. That implies angle APQ is equal to angle AQP, since by isosceles property is what I get from isosceles property. So if I take this as x and theta, then clearly I identify that if this angle is theta, this is x and this is x, then x plus theta is 180 degrees, because sum of three angles in a triangle is 180. This will be equal to 180, so that 2x is 180 minus theta. or I get x equals 90 minus half theta is what I get from sum of three angles of a triangle. So in this case, x equals 90 minus theta by 2. But we know that x is angle APQ or AQP, which is 90 minus theta by 2. Now next I consider the angle OPA. Therefore, angle OPA, as I see in the diagram, is OPQ plus QPA is what we get. Angle OPQ plus angle QPA is what I get when I split the entire angle into this angle plus this angle. So this plus this is the entire angle. So let's see what I get when I simplify further with this. That implies my angle OPQ, which I'm going to find, would be angle OPQ on the left hand side is equal to angle OPA QP. OPQ is angle OPA, which is totally which I need to find. Now let's see what angle OPQ is from here. That implies angle OPQ is angle OPA minus angle QPA is what I get when I take this to the left hand side. Now as I clearly see here, angle OPA is 90 degrees because OP is the radius and AP is the tangent. So radius is perpendicular to tangent, therefore this entirely is 90 degrees. Therefore OPA is 90 degrees and my angle QPA is x, is what I get from the diagram. But as I clearly see here, I get that my angle OPQ is nothing but 90 minus x. X is already substituted to be 90 minus x by 2, which we have already proved for x, which is 90 minus theta by 2 is what we got. So simplifying this further, I get this to be 90 minus 90 plus theta by 2. Therefore, this on cancellation gives me theta by 2, which clearly makes me understand that theta, which is angle PAQ, therefore substituting for theta, angle OPQ is angle APQ PAQ by 2. When I further simplify this by cross multiplication, angle PAQ is twice angle OPQ is what I get from the given proof. Therefore, angle PAQ is always twice of angle OPQ is how they are connected. Similarly, proceeding with the same proof, taking this angle, that is angle OQA is OQP plus PQA, and then going along the vertex Q in the similar manner, I prove that similarly I get angle PAQ or QAP is twice angle OQP, which I can prove through the similar proof. Hence, these are the two properties which are identified for the external tangents drawn from an external point A, where the angle between the tangents theta is always twice of the angle between the radius and the chord of the either angles, which I get as OPQ and OQP, which are always half of the given angle PAQ. Now let's see the last property in connecting the tangents to the circle, the extended property out here. So let's take a circle in which I want to draw for each of the point of contact. When I draw the tangents, I get a quadrilateral ABCD where the points of contacts are PQ, RS. That is, a quadrilateral which is obtained by connecting each of the tangents drawn at PQRS on the circle is what I get with the circle, of course, inside the quadrilateral, because the tangents are always outside the circle, touching the circle. Therefore, the quadrilateral obviously should lie and circle inside and quadrilateral outside. So with this quadrilateral, I would like to prove that my required to prove part out here in case of this quadrilateral is that I had to prove AB plus DC is equal to BC plus AD. That is, when I add the opposite sides in pair, they must be equal in case of this quadrilateral. So my proof is that I have to prove AB plus DC equals BC plus AD is what I need to prove in case of this. So as I clearly see here that the proof is totally reliable on an external point from where two tangents are drawn. That is, when I take each of the vertex of the quadrilateral ABCD to start with the vertex A. Now, the first vertex of the quadrilateral ABCD is clearly passing through two tangents. That is, for an external point for the circle, there are two tangents AP and AS which are equal, because we have already seen the property that from an external point the lengths of tangents are equal, therefore AP must be equal to AS. Similarly, BQ must be equal to BP. This must be equal to this, and this must be equal to this. Is how we get each pair equal to the other, because the lengths of tangents from an external point are equal. So using that condition, let's prove AB plus DC equal to this. So let's see how we can do the proof of this theorem. So considering the proof, let me consider AB plus DC on the left hand side and prove the right hand side from the LHS. So LHS being AB plus DC is what I consider, and clearly when I take AB, I can split AB as AP plus PB. Therefore, I can split AB as AP plus BP. When I add together, I get AB, as can be seen from the side AB. Similarly, I can split the side DC, because DC can be written as DR plus CR, which on the whole makes the whole of DC. Therefore, splitting DC as DR plus CR is what I get when I split each of the sides AB and DC through the respective points PQRS or P and R. Now here, AP is clearly equal to AS because the lengths of tangent from an external point A are equal. Therefore, AP is equal to AS. In place of AP, I write AS, as can be clearly seen through the lengths of tangents, this being equal to this. So AP equal to AS, I replace AP with AS. Similarly, my BP is equal to BQ with a similar property. So therefore, in place of BQ out here, I write BP. Instead of BP, I write here BQ is what I write here. Similarly, when I have DR is nothing but equal to DS, therefore, in place of DR, I write DS. And lastly, CR, which is equal to CQ, I write here CQ for each of the properties. Now next, what I do is I compare this and this and this and this. Therefore, pairing them, AS plus DS plus BQ plus CQ is what I get when I pair them alternatively. As can be seen in the diagram, AS plus DS is clearly AD on the whole, because AS and DS add up to give the side AD of the original quadrilateral. Therefore, this is in turn giving me AD, and plus this in turn gives me BQ plus CQ can clearly be seen as BC. But this, when rearranged, gives me BC plus AD, which is clearly the right hand side of the required to prove. Therefore, I clearly prove that AB plus DC is equal to BC plus AD, hence proved. is how we understand through the lengths of tangents from the external point, which make the quadrilateral ABCD from the circle PQRS. Segments of a circle. What are segments? As we have discussed about the tangents and the radius or the chord or the secant, similarly, a segment is also one of the important concepts or the property of a circle. So let's see what a segment is for a circle. So let's take a circle with center O, and let me say I have a chord AB or a secant AB to the circle. Now, what is the significance of the chord in the circle is the biggest question here. A chord divides the circle into two parts, is the other way of understanding a chord or a secant. So as we see the chord AB, this clearly divides the circle into two parts, where one of the part is this and the other part is this. Is how I get two different regions. Now, how do you understand the difference between this region and this region is very important in understanding segments of a circle. So in this case, a segment is an area which is obtained when the chord divides the circle into two parts. Therefore, I get two parts where one of the region is given by this, which is called the minor segment, and this, which is called the major segment. The reason being that this is minor in shape and this is major in shape. Now, let's see what this shaded region is called. Now, this part of the shaded region is called major segment because it is major in its area. But mathematically, how do you say that this is major in area or minor in area without actually measuring the area? Mathematically, this is called a minor segment because this does not include center of circle, but major segment always includes center of circle, is a very important note out here. So this is called the major segment. This shaded region is called the major segment because this includes center of circle. This does not include center of circle, but this includes center of circle. Therefore, this whole area is called the major segment and this whole region is called the minor segment. So the learning outcome here is that a chord or a secant plays a vital role in defining the segment of a circle. But let's take a special case. What is the special case out here? If I have a circle with center O and if my chord AB is the diameter, then what happens? How do you define the segments for a chord which is reaching up to the center of the circle, or if the chord is the diameter, is the biggest question as a special case. So in case of special case, we identify that we have exactly two equal areas. One is the major or one is the minor segment converge to become two equal segments where both are called semicircular areas. So in this case, I have each of this and each of this are called semicircular areas. And also, interestingly, if the chord tends to become a diameter, major segment will be equal to minor segment, as we have seen here. Then in this case of the special case, major segment is equal to minor segment, is what we conclude for the special case. So how do I find the areas of the different segments using the formulae is the biggest question out here. How do you find the formulae? So let's see how we can find the area of the minor segment or area of the major segment connected with the areas of the sectors. Now let's see how we can find the area of the minor segment and area of the major segment respectively. Therefore, let's use some of the geometrical properties to find area of the minor and the major segment. Before we find the area of each of the segments respectively, let me construct by joining OA and OB. Now since OA is equal to OB because they are of the equal radii, let me take the radius of the circle as R. Radius of the circle as R, and let me take the angle subtended at the center is x degrees, is what I get. Therefore, as I clearly see, the minor segment is the shaded region here. Therefore, in this case of the area of minor segment is given by area of the whole sector minus area of the triangle is what I get. So area of minor segment is area of sector OAB minus area of triangle OAB is what I get, the area of minor segment. Now as the sector minus triangle gives me this minor segment, now we have the respective formulae for the sector, which is given by its area as x by 360 times pi r square minus area of triangle OAB, which can be done with various properties like half into base into height or any other respective formula if the height is given, minus area of triangle OAB is what I get as the derived formula for area of minor segment. Next comes the major segment. Now how do I find the area of major segment? Major segment can be found, the area of the major segment can be found if we know the area of the minor segment. Therefore, area of major segment is given by the formula area of the whole circle, the entire circle, minus the minor segment gives me the area of the major segment, because this removed from the entire circle gives me the major segment. So area of circle minus area of minor segment is what gives me area of major segment. But area of circle we already know is pi r square minus area of minor segment, which I already calculated to be x by 360 into pi r square minus area of triangle OAB is what I get as the formula for area of major segment. Therefore, with these two basic formulae for area of minor segment and area of major segment connecting the circle and the triangle, we find for any situational problem where we need to find the segment which is minor and the segment which is major, finding the areas through the sector concept. This is how the formula is derived. Now let's find the area of the minor segment, which clearly makes me understand that area of waterbed, which is area of minor segment, is nothing but the minor segment, which is area of sector minus area of triangle OAB. Therefore, area of sector minus area of triangle OAB is what I get as the whole area of minor segment. Now how do we find area of sector? We all know that the formula for area of sector is x by 360, x being 90, into pi r square, that is pi r square, that is 49 times square, minus area of triangle OAB, which I need to find from here, makes me clearly understand that this will be a perpendicular drawn here, makes 90 degrees. Therefore, area of triangle OAB will be half into base into height, but I don't have the dimensions here, so I utilize the condition of finding the area of triangle using this measurement. So let's see how we can find area of triangle OAB using the given dimensions. Now clearly I see that this being 90 degrees makes this as the base and the height of the triangle. Therefore, for this right angle triangle, the area of the triangle is directly given to be half times base into height. The base being 49 and the height being 49, OB and OA respectively. Therefore, this being a right angle triangle, I get half times 49 times 49 as the base and height. So simplifying this, I get this to be 9 ones, 9 fours. So 1 by 4 times pi, if I take it as 22 by 7, this reduces to 49 times 49, and further simplification gives half times 49 times 49. Now this on further simplification gives 2 times 2, 2 11s, 7 ones, 7 sevens. Therefore, this on further simplification, I can take 49 over 2 common and then simplify with even 7 taken outside. So the rest of the terms I put there inside. So 7 times 49 by 2 is out. I have 11 inside, and then this 49 by 2 and 7 out will keep 7 remaining, which is inside. Therefore, simplifying this further, I get this to be 49 times 7 over 2 times 11 minus 7, which is 4. Therefore, this on cancellation gives 49 times 2, which is 98 times 7, 7 8s 56, 7 9 63 plus 5, which is 686 of meter square. So this is the area of the waterbed covered by the entire circular park, is how we understand. Now it is very important to note that I have taken pi as 22 by 7, but note that until and unless the problem says use pi as 3.14 or etc., you have to use pi as 22 over 7. Now using this, I have area of waterbed is 686 meters square. Therefore, my area of the circular park, which is not covered by waterbed, is area of major segment, that is indirectly to be found, is area of circle minus area of the waterbed. Area of circle is pi r square, which is clearly pi times r square, minus area of this, which is 686. This on simplification gives 22 by 7 times 49 into 49 minus 686, which on gives 7 sevens. Therefore, this on simplification gives me 686, which is written indirectly as 49 times 7 times 2. Therefore, 7 times 49, which is taken common on both these cases, gives me 22 minus 2. Now, to continue with, I got this as 7 times 49 times 22 minus 2, which on further simplification gives me 7 times 49 times 20 is what I get. To simplify this further, 7 times this is 980, and this on further simplification gives 7 8s 56, 7 9 63, 6 8 60 is meter square, is the area of the complete region which is not covered with waterbed in the entire park. So area of the circular park which is not covered with waterbed, that is the area of the major segment, is nothing but 6,860 meters square, is how we understand the areas of the segments connected with the areas in real life applications.